Recall that the Diffie Hellman key exchange is a public key cryptographic algorithm. There are some public values, so we can think also there's a public and private key. For example, in the calculations, the algorithm specifies we select a private X and we calculate our public Y, the values X and Y, and we exchange the Y with each other. So X is part of our private key, Y is part of our public key in this case. And if we exchange the values of Y with the other person, then we do a final calculation. Each side does it to calculate K, where the calculation should be that both sides end up with the same value K. So let's first just show quickly that that does happen, prove why we'll always get the same K at both sides, and then we'll look at what can the attacker do and where the strength of Diffie Hellman key exchange comes in. Our example that we introduced last lecture was we chose for simple calculations the value of Q, the prime of 353, alpha of 3, and alpha needs to be a primitive root of the prime Q. User A chooses a private value, XA, to be 97, so it needs to be less than Q. So in practice that will be chosen randomly, say by software. Then user A calculates its public Y value, alpha to the power of XA mod Q, and they got 40. And then they tell user B their public Y value and what we call the global public parameters, Q and alpha. So Q and alpha can either be exchanged in this message or maybe they were exchanged in the past. Okay, so they both know Q and alpha. And so does the rest of the world, the public values. Anyone can intercept this message and learn those three values. User B selects its own private value, 233, and calculates its public value Y. Again, alpha, the same alpha to the power of its XB mod Q, and they got 248, and tells user A its public Y value. So both sides know alpha, Q, they know their own private X, and they know both values of Y, their own public Y and the public Y from the other user. And they use the same equation to then calculate K, which is the other public Y raised to the power of their private X mod Q, and we got 160, and the other user that does the same approach but using A's public Y also got 160. Why do they both get 160? Let's look at the proof of that. It's not so hard to show that they will turn out the same. Let's write down the steps that are used. For example, YA is alpha to the power of XA mod Q. What else do we have? YB is alpha to the power of XB mod Q. These are the equations used in the algorithm, and they are known. And Ka equals YB to the power of XA mod Q. And similar, KB equals YA to the power of XB mod Q. So let's look at why those two values of K, Ka and KB, will always turn out to be the same. Let's do a substitution. So Ka equals YB to the power of XA mod Q. We know an equation for YB. YB is alpha to the XB mod q, that's yb, all to the power of xa, so just substitute for yb. And our properties of modular arithmetic, that, remember, in the simple case, 10 mod 8 equals what? 10 mod 8. 10 mod 8 equals 2. 2 mod 8. 2. 2 mod 8 again. If you keep modding by 8, you'll still get the same answer. And that concept can be applied that if you have 2 mods, something mod 8 and then mod 8 again, then in fact you can just replace that with 1 mod. You get the same answer. And similar can be applied to see that where we have exponentiation, which is just multiplication multiple times, which is just addition multiple times. When we have a mod q inside the brackets here and a mod q outside, we can actually cancel out this mod q inside because we'll eventually mod by q there. So if we mod by q twice, we can write it the same as being mod by q just once at the end. So it becomes alpha to the xb all to the power of xa mod q. And our simple rules of exponentials, alpha to the xb all to the power of xa equals alpha to the power of xb times xa mod q. So Ka equals alpha to the power of xb times xa mod q. And let's look at Kb from the same perspective, but we'll substitute, and if we'll squeeze it in, Ya is replaced with alpha to the xa mod q all to the power of, sorry, it's xb mod q. That is just substitute for Ya. And the same rules apply. That is, the mod q can be cancelled out. Alpha to the xa all to the power of xb mod q. And that becomes alpha to the xa times xb mod q. So they are the same. Alpha to the xb times xa is the same as alpha to the xa times xb. That's the proof that the two keys that we'll get on either side will be identical. Any questions? If we can reverse xa and xb, it's the same when we multiply. Where's the power? There. Then let's look at what the attacker can do. We'll look at come back to our example and see, well, given what the attacker knows, how can they find the secret? It's all about keeping K secret. So what does the attacker know? They know the algorithm. They know all those equations. What do they know in this case? Q, alpha, Ya, Yb. So we know them. We don't know Xa or Xb. They are kept private. So given what we know, let's see the steps the attacker needs to take to find the secret. for example, we start with, let's say we want to find Ka, which is the same as finding Kb, which is yb to the xa mod q. And in our example, the attacker knows that Ka, yb they know, 248, xa they don't know, and q they do know. So here we have an equation with 4 variables. 2 of them are known, 2 are unknown, so there's no way to solve that. We need to do something else. What can we do as the attacker now? We can't find Ka because we don't know what Xa is, so that suggests we look at, well, try and find Xa. We know an equation that relates, we know a second equation which says that Ya equals alpha to the power of Xa mod q. That's the other part of the algorithm. And we know Ya is 353. We know alpha is 3. We know Xa. We don't know Xa, but we know Q is... What mistake have I made? Is anyone awake? I hope you didn't copy that. 248. Alpha is 3, Xa is unknown, mod 353. Now that's better for the attacker. We have an equation with 4 variables, 3 are known, 1 is unknown. So we should be able to solve that. What's the step to solve that? We've got an exponential mod something. What's the opposite? A logarithm or a discrete log, we call it. When we have a modular exponentiation, the inverse is a discrete log. And we write it as what? The index Xa equals the discrete log, d log, all right, in base 3 mod 353 of 248. So if we can solve the discrete logarithm here, we'll find Xa, and if we find Xa, then we can easily find Ka, because we just plug it into this equation. Exponentiation is easy. If we know Xa, it's 248 to the power of Xa mod 353, and we'd find Ka. What's the problem for the attacker's perspective in general? What would make Diffie Hellman secure? If we have large numbers, these are not large numbers, if we have large numbers in terms of hundreds of bits as a binary number, then solving the discrete logarithm, we've already said, is practically impossible to do. The discrete logarithm of a number is one of those problems which is considered computationally hard. That is, if the numbers are large enough, then you cannot find the answer within reasonable time, within any practical time. So discrete logarithms, the same as factoring a large number into its primes, and the same as finding the totient of a number, those problems are considered too hard to solve. So therefore, although with these small numbers we could find the answer Xa, it'd be easy, you could do it with your lookup table. If these are large numbers, then the attacker will not be able to find Xa, and since they cannot find Xa, they cannot calculate Ka. So the strength of Diffie Hellman depends upon the fact that solving discrete logarithms is computationally hard. If you try it from the perspective of B, Kb, Yb, and so on, it's the same problem that will arise. So since we can't solve the discrete log in general, if we have large numbers, then we could try and guess XA, brute force. And again, to prevent that to be successful, we just have to make sure XA is large enough, a large random number. So if we have large enough numbers, solving the discrete log is not possible, and finding XA is therefore not possible, therefore finding the key is not possible. Any other approaches? Anything else you can do? There's maybe use B's equations. Again? All right, okay. So the algorithm is considered secure because of the dependence on the discrete logarithm. But again, always under the condition where we have large numbers. Your next homework task, which is almost ready to be released today, maybe on the weekend, will involve you using some software to calculate the Diffie Hellman parameters. Very easy, just use some software, it will do it for you. And you'll see that the length of those values are in the order of the public and private values, X and Y, are in the order of 1,000 bits, so 1,024 bits. So by large numbers, say 1,000 bits long. And that's it. Diffie Hellman is considered secure in the algorithm because it relies on the discrete log problem. Any questions on Diffie Hellman? Someone said the way to beat Diffie Hellman is to use the man-in-the-middle attack. So we've gone through an example. The algorithm is secure, but if you use it in the way that we just used it, it's possible for an attacker to do what we call a man-in-the-middle attack. Let's see how that works. Not a meet in the middle. Remember we did doubled S and we did the attack of meet in the middle. A man in the middle is different and it's applied for different attacks on different schemes. We can see it in play against the Diffie Hellman key exchange. Let's go back to what we did as our exchange here. So A sent this message to B, Q, alpha, and Y. What a man-in-the-middle attack will do is that our malicious user, let's say C, who's in between A and B, so they can intercept this message before it gets to B and modify it. So a man in the middle is, imagine that someone here receives this message before it gets to B, and they make a change to that message and then forward it on to B. And then B replies, thinking they got the message from A. B replies, and the man in the middle does another change and the message eventually gets forwarded back to A. The purpose of the attack is that that man in the middle will know the secret, and A and B think they have a shared secret that no one knows. If they can do that, then the attack is successful. Try it. Spend 5 minutes trying if you can perform a man-in-the-middle attack. So what you do is maybe go through the same steps. You can use different numbers if you like, but the same ones. But before this message gets to B, another user, let's say C, gets the message and changes YA to a value that they want. Forwards the message onto B. B thinks it comes from A. Okay, let's say the packet source address says it's from A. So B thinks they get YA, but in fact they get Y of the man in the middle. and B does its calculation, sends back, and the man in the middle changes YB to something else. See if you can do that such that the man in the middle will know the secret, and A and B think that they have a shared secret, which is the same. I'll give you 5 minutes to perform the attack. So user A chose its value of XA. Q and alpha are fixed, and we know YA, so we send the public values to B. But alpha equals 3, Q equals 19, YA equals 16. But before they get to B, think of this message that was sent. Somehow the malicious user intercepts it on the network, and they can make changes to those values. They are not encrypted or anything, so they can change them and then forward on to B such that when B receives the message, it thinks it came from A. The source address is fake to pretend to be from A. So what would the malicious user do? Change YA. Change it to what? Not any number. What value? Or how would they choose a value of Y that they change it to? They choose their own X first. Okay, that is, the malicious user does really what A did. The malicious user will choose their own X value and calculate a new Y. So they know Q and alpha. Okay, that's fixed. So they choose, let's say, an X. Anyone choose a value? 2. And they get what is it? 9. 9. Okay. They record those values. Now what's next? Send the same values of alpha and Q. Don't change them. Well, there's no need to at this stage. And modify YA to be what? 9. Right. We call it YA. It's not in fact YA. It's Y of the malicious user. Okay. But from B's perspective, when they receive the message, they think this is YA. So that's the modified. Then see what B does. Try what the steps B would take and then what they send back, and see that what the malicious user does then. Try and complete the steps. B, when it receives the YA, it calculates, after selecting its XB, it calculates its YB and sends back to A. So let's do that. B, let's say they choose XB. Their private value, a number, 11. Calculate YB. What do they get? 10. So that's 3 to the power of 11 mod 19. You look it up, you get 10. And now we'll send back YB. And we should also calculate KB. How do we calculate KB? YA to the power of XB mod Q gives us, that's a 19, gives us what? 5? Okay, so that's the K from B's perspective. What does the malicious user do? It needs to do a couple of steps here. It can calculate K. All right, let's call it, to be more specific here, let's call this X malicious B and B. They're the ones we're using with B. So we receive YB and we calculate, let's say K that B has. How? We take YB, the B received from the other person, raise it to the power of our private X, X mal B, there's 2 that we chose, mod 19. What do we get? Sure? Look it up. 5. It should be 5. I just want to make sure that I've done it correct. So, here the malicious user knows KB is 5. B thinks the shared secret is 5. So we're halfway there from the attack's perspective. What we want to do is allow A and B to send and receive the messages as they expect. That is, A sends those 3 values, B receives 3 values, B sends back Y, A will eventually receive Y. They'll do their own calculation of K, and let's see what happens at the end. The malicious user now was going to send back. What's it going to send back? YB, that's what A is expecting. But they actually select their own value of X. Let's say 7. And if we use 7, what will Y be? 7 alpha, so 3 to the power of 7 mod 19 is 2. So what do we send here? We send 2. And in addition, the malicious user can calculate Ka alpha, sorry, not alpha, Y received from A, 16, raised to the power of our private value, 7, mod 19. What do we get? You're my calculator. 17. Hopefully this works. What does A do? They receive YB. I think I got a message from B. We calculate Ka. We take the received YB, 2, raise it to the power of our X value that we started with, 10. 2 to the power of 10, mod 19. What's the answer? 17. What the end result is, A and B don't know the malicious user did anything, because from their perspective, A sent those 3 values and then it received a Y value back. It doesn't know they were modified. And similar, B received these three values. Okay, I receive Y from A. I calculate my KB and send back my Y value. It doesn't know anything was modified, but the malicious user, the man in the middle, actually did these modifications and used their own values. So the result from A and B's perspective, they think they have exchanged with each other the values, and they think the key that they have is the same that the other side has. We know it's not. So A thinks that the secret value is 17, B thinks the secret value is 5. The malicious user knows both of those values. It knows KB is 5, the one that B thinks is the secret value, and KA is 17. What happens next? Let's say now we encrypt using DES or AES using this secret key. A sends an encrypted message to B. A encrypts with the key 17. It thinks B has the key 17. It sends, the malicious user intercepts again. The malicious user can decrypt because they also have the key 17. They get the plain text. They encrypt it again using key B, 5. Forward on to B, B decrypts. It successfully decrypts because B thinks that the key is also 5. A and B send a message to each other, encrypted, but in fact the malicious user has intercepted and decrypted the message in the middle. Just to illustrate that final step. So that's the key exchange, but how is it useful? Let's say we now encrypt a message with some symmetric key cipher. For example, we encrypt using key 17 some message and send that ciphertext. So this is the key that was used to encrypt. The malicious user can decrypt. So that, let's be precise, that's the ciphertext, C. So they can decrypt because they also have the value 17. And now they learn the message, M. So they now know the encrypted message, and what they do is they encrypt M and forward it on to B. C prime, I'll call it, because it's different from the original C. Encrypt, use the same message using what? The key 5. B receives. It's got a message from A. It thinks it shared a secret key with A, which is the value 5, so it decrypts using the key that it shared with A, and it gets the original message. It successfully decrypts, so everything works as expected from B's perspective, and they get the message. But what has happened is that the malicious user also knows the message. So this is the man-in-the-middle attack where A and B think they're communicating securely. They think they have a shared secret key, but in fact they have a key shared with a man in the middle. And now the man in the middle can intercept anything that they send to each other, decrypt it, and see the message. They could also modify the message if they wanted to. So this is a common form of attack, not just on Diffie Hellman, but on other, especially public key ciphers. We'll see it applies on RSA if it's used in some scenarios. Any questions on the man-in-the-middle attack? Or it could be a woman in the middle. It's whoever's doing the attack. Of course, this requires the malicious user to be able to intercept and modify messages, which in a network normally we assume they can do. Okay. How do we stop it? What service do we need to stop this? What went wrong? One of the first steps was that B received a message, this first message here, thinking it's from A when it's in fact been modified. The malicious user has modified it, so it's actually come from someone else. But B thinks that they received this message from A. So what we need is the service of authentication and data integrity. We need to be able to prove that when we receive a message, who it came from. So what we'd need is when B receives this message, it should be able to detect, this is not from A, it's from someone else, therefore don't trust it. And that's, in general, authentication. So we need to be able to authenticate the messages we receive, not just trust anything we receive. And that's our next topic. To close on public key cryptography, we may see another example of man-in-the-middle on another cipher in another topic. The countermeasure is to use authentication, and we'll see in the upcoming topics the main form is digital signatures or combination with public key certificates. So we'll introduce them. We've already said that there are other public key crypto systems. We've gone through RSA and Diffie Hellman, but there are others. And that finishes this topic.